everyone, and welcome back. I wanted to do a couple of videos about vectors because they are a very important part of physics and are dealt with in relation to a number of physics variables. So to get us started, there are two types of variables in physics. A scalar is a physical quantity that has only magnitude but no direction. Examples of scalars include time, mass, energy, speed, and distance. So, for example, if you were to ask someone, how long is it going to take you to do your homework? And they said 2 hours to the east. That answer doesn't really make sense. Same thing if someone said 5 kilograms up. Speed and distance are related to variables that are vectors, but speed and distance by definition do not include the actual direction, so they are scalars. Vector. A vector is a physical quantity that has both a magnitude and a direction. We've already dealt with a few of these. Velocity we've dealt with, acceleration we've dealt with, displacement we've dealt with, force is going to be the big one, and momentum will be coming up later on. A side note, we've already dealt with force and velocity vectors quite often, but what I'm going to teach you about vectors in this video and the next one, the technique is the same for any variable that is a vector at all. Typically, when you're dealing with vectors in physics, what you're trying to find is called the resultant vector, a vector representing the sum of two or more vectors. We have already talked about this in relation to net force. Net force, by definition, is the vector sum of all forces exerted on your system. Some visual examples. What I have in blue here are the component vectors, and the red vector here is a resultant. Now, this is a typical two-dimensional vector breakup. However, it does not have to be that pretty. Here are my vector components, and my resultant is from start to finish. So these blue vectors, they could be displacements, forces, accelerations, anything that is a vector. So a few rules. Number one, vectors can be added in any order, but they must be added tip to tail. Let me show you what I mean. So here I have two examples. I have my component vectors, which are blue, green, violet, and brown. I combine these tip to tail like train cars, and I get this red resultant vector from start to finish. If I put these component vectors in a different order, violet, brown, blue, then green, they will still produce the exact same length and direction resultant vector as long as they are tip to tail. The component vectors can represent the path taken, and the resultant vector is from start to finish if these were displacements. Okay, this slide is about naming nomenclature. On this slide, I have four vectors. 1, 2, 3, 4, these four blue vectors. And I have these 8 letters. Take a look at this blue vector in the upper right. If I asked you what direction that vector is pointed in, you may say to the upper right, or if this was mapping, you might say northeast. However, for physics, that is definitely not good enough because you need to give the exact direction of your vector if it is at an angle. And here is how to do the proper nomenclature. We are going to start with the letter A here. Let's say our angle was between the x-axis and this blue vector. How you would state this using axes is you would state above the positive x-axis. So literally, you would use the positive axis as your base, and this vector is pointing above the right, above the positive x. In mapping nomenclature, this would be called north of east. Notice that the major axis that the vector is off of is always said last. So let's say A was 30 degrees. You would say 30 degrees above the positive x-axis. Or if it was mapping, 30 degrees north of east. Now, you can state this vector off of the positive y-axis as well, because B is an angle off the y-axis. If you're going to state it off the y-axis, you would say either to the right of the positive y-axis or east of north. So if A was 30 degrees, B would be 60 degrees, and this would be 60 degrees right of the positive y-axis or 60 degrees east of north. Following these nomenclatures around, this vector to the left of the y-axis, you would say left of the positive y-axis or west of north. D would be above the negative x-axis or north of west. E would be below the negative x-axis or south of west. F would be to the left of the negative y-axis or west of south. G would be to the right of the negative y-axis or east of south. And H would be below the positive x-axis or south of east. So this would be a good slide to take a screenshot of and keep somewhere. Side note, for most situations, The axes version should be accepted even if you're using mapping, because the axes version is based solely on whatever point of view you're using. So if you said above the positive x-axis and it's a map, people know that east points to the positive x-axis. However, you can only use the mapping nomenclature if the problem has mapping in it. In other words, if the problem actually states north, south, east, or west. The reason for that is if you're looking at something from a side point of view, let's say a ball is dropping, you're not going to say the ball is falling south, because it's not. It's falling toward the ground. It is falling the negative y direction. In other words, if I asked you to walk south, you're not going to get a shovel and start digging. So the axis version should be able to use anywhere, and the mapping version can only be used with mapping problems. Okay, let's do a couple problems that actually involve vector addition. We'll start with this one. If you leave your house and walk 3 kilometers east, 5 kilometers north, 12 kilometers south, 6 kilometers west, and 3 kilometers north, what is your total displacement relative to your house? Now, one of the ideas here is actually to get an understanding of how much east and how much west you've walked and how much north and how much south. And I know for this problem, for what I'm about to do, you can probably do it in your head. But I'm going to show you a technique that's going to be used in higher level problems just to show it to you, and it's really going to be put to use in my next video. So on the right, I'm going to have a table which I'm going to put to use, but first, the more important thing is on the left here, here's my little house. And I am going to draw these vectors. And I'm going to try to keep the size to scale. So the first movement is 3 kilometers east. 1, 2, 3. 3 kilometers. 5 kilometers north. 1, 2, 3, 4, 5. 12 kilometers south. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 kilometers west. 1, 2, 3, 4, 5, 6. And 3 kilometers north. 1, 2, 3. Which means my resultant is going to be from here to here, start to finish. And I'm going to want this angle, because you always want the angle from where the vector starts, not where the vector ends. So I want to know the magnitude and direction of this displacement start to finish. Again, since all these vectors are right on the axis, it's kind of a lower level problem, but I want to show you the higher level technique with this anyway. I'm going to label all these vectors. Label this A, B, C, D, E. I'm going to take them, I'm going to put them in my table here. So I have the x-axis and y-axis, and I already have the units here in kilometers, so I'm not going to bother with the units in the table itself. A is 3 kilometers to the east, nothing on the y. B, nothing on the x, 5 kilometers on the y. C, nothing on the x, negative 12 kilometers on the y because it's downward. D, negative 6 on the x because it's to the left, nothing on the y. E, nothing on the x, and positive 3 on the y. Then I'm going to get my total. On the x, I have a total of negative 3 kilometers, and on the right, I have a total of negative 4 kilometers. So I'm going to take my total information here and then make a final resultant of it. You do not have to do the final resultant in your drawing, because this one came out kind of neat, but some of them may look a little messy. So I'm going to do my resultant in an open area. So I'm going to make a little start point right here. On the x-axis, I'm going 3 units to the left, which is 3 kilometers, and then 4 units downward, 4 kilometers. I am not putting negatives on my vector drawing because my arrows speak direction. And one more thing I would like to note, and this is actually kind of important. When I show you the slides, my component pieces were recognized by color. However, if you're just doing this with a pencil, your pencil doesn't change colors. So how your vector components are recognized are, your components should always be dashed lines. Your resultant should always be a solid line. That is how your professor or grader recognizes that you recognize the difference between component vectors and your resultant vector. So looking at this, I have a right angle right here. And I can either do Pythagorean's theorem, or this is a 3, 4, 5 vector breakup here. And I want this angle, which means I'm going to use inverse tangent. So theta inverse tangent, 4 over 3. The units would cancel, and I would get 53.1 degrees here. Now, this vector would need to be stated, and here's how you would state it. This would be 5 kilometers at 53.1 degrees. And since this problem used mapping, I can use mapping, and this would be south of west. Or I could use below the negative x axis. Side note, I also could have gone down and to the left to combine these vectors tip to tail, because that's the rule. This would be 4 kilometers. This would be 3 kilometers. They can be added in any order, but they must be added tip to tail. Down and to the left still obeys those rules, which means I also could have gotten the answer 5 kilometers at 36.9 degrees. And my angle alpha here would be west of south or right of negative y-axis. So either of these answers would be correct because they both are the same size and point in the exact same direction. The only difference is one of them is based off the west axis and one of them is based off the south axis. But both of these answers are perfectly correct. All right, let's do one more. And concerning with vectors, you'll probably be dealing with forces more than anything. So let's take a look at this one. There are 4 forces exerted on a ball. A 50 Newton force is pulling downward, a 20 Newton force is pulling to the right, a 30 Newton force is pulling left, and an 80 Newton force is pulling it upward. What is the net force on the ball? Typically in a force diagram, you should have labels and names, but for the sake of this lesson, I'm specifically just dealing with vector addition here, so I didn't bother. However, I am going to try to keep the size of the vectors appropriate. So 50 newtons pulling downward. I have 80 newtons upward. I have 20 newtons to the right and 30 newtons to the left. It doesn't have to be perfect, but you can easily tell by my drawing, even if there are no numbers here, as far as the magnitude of what these forces would be in relation to each other. So I'm going to shorthand this. Left and right, I have a larger force to the left, 30 newtons left, 20 newtons right. So my first component to the left would be 10 newtons. Up and down, I have a larger force upward. 80 minus 50 is 30 newtons. So my resultant is from start to finish. I'm going to move the 10 newtons down here so I can have room because I want this angle, the angle where my vector starts. So using Pythagorean theorem, I would go after my resultant, which happens to be my hypotenuse here. Then this would be 31.6 newtons. I need to get this angle. Again, inverse tangent is your friend. It'd be 30 over 10. The units would cancel. And I want to get an angle of 71.6 degrees. So the net force on this ball would be 31.6 newtons at 71.6 degrees above the negative x-axis. Or if I got this angle, I would get 31.6 newtons at 18.4 degrees left of positive y. Both of these answers would be correct for the net force. However, in this case, it would be completely inappropriate to use mapping because none of these directions are north, south, east, west. So if I used mapping here, that nomenclature would literally be incorrect. So I hope this video on vector addition has helped you out. My next video, I'm going to do a more complicated problem. Have a good day. This is Mr. M signing off.